Okay, hello again. We're going to move on to our new material now. And I'm excited to tell you that this is our last section of new material. This week we're going to finish up chapter 15. We're not going to get to chapter 16. And next week we'll just do review, and then we'll start doing review for the final as well. So, fasten your seatbelts. Here we go. We're going to continue on talking about kinetics. Okay, now we said that the rate of a reaction is affected by temperature. So why doesn't temperature appear anywhere in the rate equation? Okay, because rate is the rate constant times the concentration of the first times the concentration to the second, both to their respective orders. So if rate is dependent on temperature, why doesn't it appear anywhere in this equation? Well, if you remember, this rate constant is different for every equation, and part of the reason it varies is it varies based on temp. So the temperature is already accounted for in this rate constant. Okay, so as the temperature increases, the rate constant gets bigger because remember, it's proportional. So as temp increases, K increases. And then the reverse of that is as the temperature decreases, the value for K will decrease, okay? So we're not going to get into actually how they come about K taking temperature into account because the math is a little bit beyond this class. But just remember, as the temperature increases, K will get bigger. As the temperature decreases, K will also decrease. And the temperature factor is already kind of baked into this value for K. All right, another way to think about it is activation energy, another way to think about activation energy is to think about the energy that's required. So we talked about activation energy in the last module, or in the last chapter. So another way to think about activation energy is it's the energy a reaction needs, or the energy required to make effective collisions. Because remember, a reaction will only take place, I can't talk and right at the same time, effective collisions. Okay, because the only way for the products to actually be made in any reaction is to have effective collisions among the reactants. Okay, so if a reaction has a low activation energy, the temperature doesn't need to be very high to get an effective collision. Okay, but if a reaction has a high activation energy, the temperature must be high to get effective collisions. Okay, so at a low temp, at a low temperature, like if you look at the picture on page 467, at a low temperature, the first reaction will have more effective collisions than the second reaction because it has a lower activation energy. So again, I'm looking at the picture on page 467. Okay, so at a low temperature, the blue reaction will have more effective collisions than the red reaction. Okay. Therefore, the rate constant for the blue reaction is a bigger number than the rate constant for the red reaction. Okay, so these are two different reactions, the blue and the line. The blue reaction has a lower activation energy than the red reaction. So at the same temperature, say at this temperature of 250 Kelvin, there's much more effective collisions taking place for the blue reaction than there are for the red reaction. Okay, another thing that we're going to talk about in this chapter then is we're going to talk about catalysts. Okay, so what is a catalyst? Okay, a catalyst is a way to speed up a chemical reaction. So another way to speed it up is to add a catalyst to it. The catalyst increases the rate of a reaction, but it doesn't get used up in the reaction. Okay, so in other words, if you had reaction where you had A plus B plus a catalyst, A and B would react and would give you products C and D, but at the end, you would still have the catalyst as a product. So it would be a reactant and a product. The catalyst does not get used up in the reaction, but by adding it, we make the reaction run faster, okay? We are not able to do experiment 15.2. because I don't have the chemicals at home, I don't have the equipment at home, and obviously you don't either. But I'm going to try to walk us through what happens in experiment 15.2. There won't be a lab report on this or anything, but I'm just going to try to walk through this and explain what's happening. Okay, so in 15.2, we have 2 beakers. Okay, I have a 100 milliliter beaker. And I have a 250 milliliter beaker, so it's bigger, okay? All right, and to both of these, I'm going to add some yeast, okay? So I'm going to add some dry yeast down here. And in this one, I'm going to add 0.2 grams of yeast. And in this one, it's a bigger beaker. I'm going to add more yeast. I'm going to add 3 grams of yeast. All right, so now I have 2 beakers, yeast in both of them. Yeast is a solid. To my larger beaker, I'm going to add in 50 ml of hydrogen peroxide, okay? And when I do that, what I'm going to see is a bunch of bubbles forming, okay? So bubbles forming, we would see that all over if I did that. To my smaller beaker, I'm also going to add 50 milliliters of hydrogen peroxide, okay? And I'm going to watch what happens, and I will see maybe a couple bubbles form, but not a whole lot, okay? Not very fast. So 2 beakers, they each had yeast in them, but different amounts. I added the same amount of hydrogen peroxide to each. The larger beaker created a bunch of bubbles. The smaller beaker created just a few bubbles. So then if I could, I was going to let these beakers both rest until the next day. So these things will just keep reacting until the next day. And if I let them sit on the counter and then the next morning I got up, what I would see is 2 beakers with some solution in each, and there would be some solid on the bottom of each. Then I would add yeast to each and look for more bubbles. So the next day I would add more yeast to each of these. and and try to see what would happen. But what I would notice is that the second day, when I added more yeast, I would not get any more bubbles. So second day, add more yeast, but there would be no additional bubbles. So why is that? Why did that happen? It seems like if I would add more yeast, the reaction would go again and I would end up getting more bubbles. Well, what happens here is that yeast is the catalyst. Okay, and that's why the second day when I came back, I could still see the yeast in the bottom of the beakers, okay? It was not getting used up. The yeast just made the decomposition of the hydrogen peroxide go faster. Because it's a catalyst, it increased the rate. That's why when I had more yeast in the larger beaker, I saw more bubbles, because the reaction was happening faster. Because I had a smaller amount of yeast in the smaller beaker, the reaction was still happening. The hydrogen peroxide was still decomposing. It was just doing so at a much slower rate. But when I let these sit overnight, both of the beakers, the hydrogen peroxide in both of the beakers completely decomposed. This one just happened fast, which is why we saw a bunch of bubbles in the very beginning. This one happened much slower. But overnight, because in both beakers, the hydrogen peroxide completely decomposed, when I added more yeast, I didn't get any more bubbles because remember, yeast is just the catalyst. It wasn't actually taking part in the reaction. Okay. Now, yeast is a unique thing. Yeast is actually a living organism. And anyone that's ever done any baking has seen this. To activate yeast, you have to give it sugar for food, and you have to put in usually some warm water. And that kind of livens up the organism and gets the yeast going. Well, yeast contains something called catalase. Okay? And catalase was actually the catalyst in our experiment, in our virtual experiment on paper. Okay? And catalase decomposes, so this substance decomposes oxidizing agents. Okay, and that's a really good thing because oxidizing agents are notorious for destroying life. Okay, these oxidizing agents destroy chemicals that are necessary for life. So if we have too many of these oxidizing agents, they can actually destroy life. Okay, so just like yeast, guess what else produces catalysts? You produce catalase. And again, it's a good thing you do because it keeps the oxidizing agents in check so that our life can continue, okay? And it also explains why hydrogen peroxide, just like it caused the yeast caused the hydrogen peroxide here to decompose and bubble up, that's why when you put hydrogen peroxide on a cut, it also bubbles. So hopefully you've all had this experience where you've cut yourself and your mom has put hydrogen peroxide on it. There's a picture of it happening on page 471, okay? So what happens when you put hydrogen peroxide on a cut is the hydrogen peroxide mixes with all the fluids in the wound. And guess what? Those fluids include the catalase in your body. Okay, so not only is the hydrogen peroxide mixing with your blood and your plasma, but it's also mixing with your catalase. Your wound starts bubbling, just like the beakers. Again, those beakers that we talked about had yeast in them. Yeast has catalase. So when we mix the hydrogen peroxide with the yeast, it bubbled. Well, now we're mixing hydrogen peroxide with the catalase in our body and the wound bubbles. Okay, so the wound bubbles because the hydrogen peroxide and the catalase are mixing. Okay. The hydrogen peroxide then decomposes, just like it was doing in the beakers, into water and O2, and that O2 is what you see that's causing the bubbles. Okay? The hydrogen peroxide that doesn't decompose is left to kill the bacteria. Because remember, the catalase decomposes oxidizing agents, which destroys chemicals necessary for life. Well, we want these bacteria chemicals to be destroyed. So the hydrogen peroxide that doesn't decompose is actually left then to kill the living bacteria. Okay? So the hydrogen peroxide that doesn't decompose is oxidizing the bad bacteria in your wound, and that's what disinfects your wound. Okay? So the bubbling part is actually not doing the disinfecting. The bubbling part, it's what's mixing with your catalase, okay? The part that's left over that's not currently bubbling is actually the part that's disinfecting your wound, because the hydrogen peroxide is oxidizing the bad bacteria. Remember, bacteria is a living organism. So it's oxidizing the bacteria, which kills it, and that's what's doing the disinfecting. Okay, so hopefully this wasn't all too confusing and our little virtual lab wasn't too confusing, but read through it in your book, and hopefully the second time through it'll sink in a little further. Okay, so let's talk a little bit about how catalysts work. So why does adding catalysts make the reaction go faster? Well, what they do is they lower the activation energy. Okay, so remember, the activation energy is what we need to get a reaction started. Okay, So catalysts lower the amount of energy required to start the reaction. So again, they don't take place in the reaction, they just lower the amount of energy needed to get the reaction going. Okay? So if a reaction has a low activation energy, that means it has a high value for K, the reaction constant, which means it will have a high rate of reaction. Or a fast, okay? So a low activation energy means a big value for K, which means a fast reaction. Okay, and a catalyst lowers this activation energy, which then leads to a faster reaction. So that's how a catalyst works. This is where the catalyst is working. It's working on this piece, and if it can lower this activation energy, it can make the value for K bigger, which then makes the reaction rate faster. Okay. Another way to look at this is if we look at the figure on page 472, again, this is now the same chemical reaction. The blue chemical reaction is done without a catalyst. The red line is done with a catalyst. So you'll notice that with the catalyst, the activation energy, which is the height of the hill, is much lower on the red trial than it is on the blue trial. You'll also notice that in both cases, the products are here at the start. The reactants are here at the start, the products are here at the end, and the total delta H between them is the same. It's just, a catalyst just affects the activation energy, which is that hill. So it's the same reaction, just done at different rates. Okay. Now there are two different catalysts that we are going to study, one in more depth than the other. So the two different catalysts are homogeneous catalysts and heterogeneous catalysts. And again, you know, homo means the same, hetero means different. So a homogeneous catalyst is where the phase of the catalyst is the same as the reactants. And down here, a heterogeneous catalyst is where the phase of the catalyst is not the same as the reactants. Okay, so there's probably different permutations of this, but we're going to keep things pretty simple for our study, okay? So as far as we're concerned, all the reactants will be of the same phase, and either the catalyst will be a different phase or of the same phase or a different phase, okay? So he's not going to throw you a curveball. So let's look at homogeneous first, a homogeneous catalyst. Okay, so let's consider the decomposition of ozone. Okay, so ozone is this O3 gas. And when it decomposes, it turns into just O2 gas, which we're very familiar with, okay? So just to balance the chemical equation, I have 2 molecules of ozone and then 2 molecules of O2, or 3 molecules of O2 gas. Now this reaction on its own with no help is very slow. okay? But we can speed this reaction up if we add nitrogen oxide as a catalyst, okay? And if we do that, we end up getting 3 steps that when taken together give us this overall reaction. Okay, so step 1 is we are going to add the nitrogen oxide, monoxide, to the O3 gas. And when we do that, that will yield nitrogen dioxide gas plus O2 gas. Okay? In step 3, we have our O3 gas decomposing into O2 gas plus just a single oxygen gas. And this reaction actually takes place because of the sun. And then finally, our third step, we have nitrogen dioxide gas plus the O that was created here. And those two yield nitrogen monoxide gas plus our O2 gas, okay? These 3 steps together all happen faster than this single equation here, yet they yield the same thing. Okay, so let's see why that is. Okay, we added nitrogen monoxide here, and as you can see, in the end, we end up with nitrogen oxide here. Okay, so we added it, and then it ended up as a product. It kind of went through some iterations in the middle, but from step 1 to step 3, we end up with nitrogen monoxide. Okay, here we made nitrogen dioxide, right? But then it got used up in step 3. So this kind of netted, we made it and then we used it up, okay? The same thing with just our oxygen. Here we made the oxygen, but then we used it up, okay? And again, we added nitrogen monoxide, but then in the end, we still had the same amount of nitrogen monoxide left over, so it kind of netted 0. So in the end, the only reactant that we had is O3. We have our O3 reactant here, our O3 reactant here, and both of these netted 0. So in the end, the only reactant we had was O3. The only products we have, well, the only product left here is O2 gas, the only thing left here is O2, and the only thing left here is O2. And this is where I'm saying these 3 steps net to this equation that we wanted to happen in the first place. It's just these 3 reactions can take place faster than one of this. And again, the reason I crossed some of these out is because here I added it and then here it's a product, okay? So it nets to 0. Here it's a product, but then in step 3 it gets used up. So really, we made it, then we used it up. So there's nothing net on either side. The same thing with just the plain oxygen. Here we made the plain oxygen, here it was used up. So in the end, there's none of this left over, okay? Then I looked at what reactants are we left with, what products are we left with, and it ends up being the very same reaction that we wanted. And again, all 3 of these happen faster than this. But what made them happen faster was the addition of the nitrogen monoxide. Okay. all three of these things taken together, this is called the reaction mechanism. Okay, so these three steps are called the reaction mechanism. All right. Let's look at another example of this. Let's look at example 15.4, just to help solidify what we're talking about here. So I'm on page 473. Example 15.4. It gives us a reaction mechanism, and the reaction mechanism has the following two equations in them. I have S2O8 negative in aqueous solution plus 2 iron ions, iron plus 2 in an aqueous solution. And when those two react, they produce 2 SO4 ions plus 2 iron 3 plus ions. Okay, so this is one reaction, the first reaction in our reaction mechanism. Then I have a second reaction where I have 2 Fe3 plus ions in aqueous solution plus 2 iodine ions in aqueous solution. And when these two react, I yield 2 Fe2 plus ions plus I2 aqueous. Okay, so these two things together are my reaction mechanism. Which means both of these reactions are going to take place. This is going to happen, and then as soon as this happens, this reaction is going to happen. Okay? And the questions are, what is the catalyst? And what is the net reaction? I call it net reaction. They say, what is the reaction being catalyzed? Catalyzed. And to me, this means like, what is the net reaction? All right, so let's start by looking at everything. All right, so I'm going to look for common things, common molecules, okay? So here I have a S2O8 negative, and I don't see that anywhere else, okay? Here I have 2 iron 2 plus ions, and then look, over here I have 2 iron 2 plus ions. So let's make note of that. How do I want to say this? I add 2 iron 2 plus then I make 2 iron 2 plus. Okay, so here's what I'm talking about. I added them here, and I still have them left here. Okay, so here they're a reactant, here they're a product. So they kind of negate each other, reactant, product. They net to 0. I keep using that phrase that they net out. But I guess you could say they cancel each other. Here they're a reactant, here there's a product. Okay? Let's see if I can find any more things like this. I have 2 SO4 negatives. I don't see any more of those. I have 2 Fe3 pluses. Oh look, I have 2 Fe3 pluses here and 2 here. So here I made 2 Fe3 plus ions, and then I used up 2 Fe3 plus ions. I don't need a different color. So here, the first step in our reaction mechanism made 2 of these ions, but the second step in our reaction mechanism used them up. So again, this product cancels out this reactant. All right, let's look and see if I have any more. Here I have 2 iodine ions. I don't see that anywhere else, and I don't see this molecule anywhere else. Okay, so I've identified both things that were made and then used up, or added and then still left at the end. All right, so which one of these is the catalyst? Remember, a catalyst is something that's added to a reaction, but it's never used up. Well, I can see here my Fe2 plus was added, but in the end it was not used. So my catalyst must be the Fe2 plus aqueous. Okay? This Fe2 plus has to be my catalyst because I added it in the beginning, in the first step, and in the end, I still had it left. Okay, it kind of took place in some of this, but in the beginning I added it, and at the end it was still left over. Okay? So we answered the first question. Then I want to know what reaction is being catalyzed, or what is the net reaction? Well, to determine that, I just leave out all of the molecules or ions that cancel each other out. So on the product side, I have S2O8 negative aqueous. That's my only product in step 1. My product in step 2, I have 2 ions aqueous. Okay, so those are my only 2 products that I have left. Or, sorry, my only 2 reactants. And then I do the same thing on my product side. Products that weren't canceled include this 2SO4 negative 2 aqueous. This one was canceled, and then my products over here, this one canceled, but my I2 was left over. Okay, so this is my net reaction, or the reaction being catalyzed. And if you'll notice, it's even balanced. Here I have 2 sulfur, here I have 2 sulfur. I have 8 oxygen. This makes 8 oxygen, 2 iodine, 2 iodine. Okay? So to figure out what reaction's being catalyzed, I just omit the molecules or the ions or the atoms that are canceling each other out. They're on both sides, a product and a reactant. Okay? And then these are all my remaining reactants. And these are my remaining products. So I hope that makes sense. Okay, finally, we are going to look at heterogeneous catalysts. I'm going to have to use another one of these pages just turned over. Okay, heterogeneous catalyst then is in a different phase. Heterogeneous catalyst is in a different phase than the reactants. And I should go back and look at this. You'll notice here my reactants were both in the aqueous phase, and my catalyst was also in the aqueous phase. So this was a homogeneous catalyst. I should have pointed that out earlier. My reactants are aqueous, and my catalyst was aqueous. Everything in this reaction mechanism was aqueous. So that was a homogeneous catalyst. Now we're talking about heterogeneous catalysts, and this is where they're in a different phase than the reactant. Okay, now these, while a homogeneous catalyst actively participates in the reaction, it just doesn't get used up. These don't participate in any reaction. Okay, a heterogeneous catalyst does not participate. But what it does is it forces the reactants to get close to one another so that they can react. Well, I should say so that they can collide and react. Okay? So a heterogeneous catalyst just forces the reactants to get close enough together that they can actually collide with each other, and then they will react. So they provide the condition for the reaction to take place. Okay? So how do they do this? Well, a catalytic converter in your car, I don't know if all of you have ever heard about that, but a catalytic converter is a piece of equipment in your car, and it acts as a catalyst. And what it does is it helps convert the carbon monoxide, which is really dangerous, but it comes from your exhaust, so your car is creating this carbon monoxide in your exhaust. It helps convert it to carbon dioxide, which is already in the environment. It's much less dangerous. Okay, so it helps this reaction happen. And I guess to balance this, I need to do this. Okay, so this is carbon monoxide created by your exhaust. This occurs naturally in the air. This is dangerous, so we want it to react with the oxygen to create carbon dioxide, which is not as dangerous. Okay? So we want this reaction to happen. The problem is this reaction would happen very slowly. It would not create, this here would not create very many effective collisions. So if you look on page 472, no, not 472, 474, you will see how a catalytic converter works. So this is a picture of a catalytic converter. A catalytic converter is a solid piece of mesh. So these blue dots down here represent a solid piece of mesh. Again, in our reaction, our carbon monoxide and our oxygen are gas molecules. So obviously they're in a different phase. So the catalytic converter is a solid mesh, so it's a heterogeneous catalyst. And what happens is the catalytic converter, this mesh here, attracts these molecules to it. So these molecules are drawn to the mesh. And when they're in the mesh, then they become close enough so that they can react together. Okay? So the mesh catalytic converter isn't really taking place in any, it's not reacting at all. It's just providing a condition for these molecules to get close enough to actually react with each other. All right? And that's about as much as we're going to look at heterogeneous catalysts. Okay? So you just need to understand that they don't really participate in the reaction. They just force reactants to get close enough so that they can actually react with one another. All right? Here in our our homogeneous example, this iron 2+ ion was actually participating in the reaction. It's just it was coming out as itself in the end. Okay? And that's it, guys. We are at the end of chapter 15. So we are at the end of all new material for this year. So this week you're going to finish module 15. You'll do the comprehension checks, the review questions, all that you usually do. The following week then we'll have a test over module 15 and then just begin studying for the final exam. So again, if you have any questions, you know the routine, put them out on Google Classroom. I hope you guys are all doing well, staying safe. I miss seeing you face to face, and I'm sorry if this hasn't been the ideal way to finish up the year in chemistry, but hopefully all you are getting through, and we'll just plan to talk to you soon. Thanks.